Hi there, this is part 2 of my solutions for the topic 610 review set, the paper 2 style questions, starting with number 9. First, we're asked to draw a free body diagram for the mass that is stationary as the rotation is taking place. We obviously have the weight. Since the man isn't falling, something must be balancing his weight, which would be the force of friction. We know force of friction would be the frictional coefficient times the normal force. So there must be a reaction force from the wall, and that's it really. This act will end up providing the centripetal force, because this is the circle, a horizontal circle that the man is moving on. The force that acts towards the center of that circle, which is the reaction force from the wall, is the centripetal. The reason why there is normal force pushing the man in towards the center is due to the man's inertia. As he is rotating, he's in a linear velocity being tangent to his circular path. That would make him want to move in the horizontal direction that he is instantaneously moving, which means the wall pushes back inside to constantly change his direction of movement. So in 9b, we're asked to show that the minimum angular velocity omega is given as that. So we know that in this kind of command term, in show that questions, this is our strategy. We have to start with formulas from data booklet and end with this. So how do we do that? We find first what are the variables I'm asked to relate to end up with this expression. So we have the coefficient of friction, we have radius, we have g, and we have the angular velocity. So things we know that involve the coefficient of friction, well, it's obviously included in here, where force of friction is equal to coefficient times the normal. And we also know in context, the normal force is providing the centripetal. So what I do will be setting the normal force equal to the expression for any centripetal, which would be mv squared over r. And I can rearrange this for the normal force as well and write it as the force of friction divided by mu. Now, since these are both expressions for the normal force, I can now set them equal to each other. So I'll write that right here. Force of friction divided by the coefficient will be equal to mass v squared over r. So how do I go from here to here? Now we know the relationship between v and omega is r omega, so I can substitute that in there. And since vertically this person is in equilibrium, I know force of friction is equal to mg. Now rewriting this expression again, I would have mg divided by the coefficient of friction in here, and m times r squared omega squared, because I'm squaring the v and this is v, divided by r. Then I divide both sides by m. I can divide this side, I can cancel these r's, and then all I have to do is rearrange this for omega, and omega squared would be equal to g over, I'm bringing this r down here, so mu times r, and then to get the omega, square root of this is giving me the function that I want. So 9c actually asks us to use that expression. So in a lot of IB questions, you will see that first you're asked to derive or show that a given expression like we just did, and then the next part actually asks you to use that expression. So even if you can't solve this previous part and show the algebra to get there, you have the expression to solve the next question given in the previous part. So now we're supposed to use this. We know g, we know mu, and we know 3.5 meters. So that calculates to 2.6 radians per second. This is simple substitution of the given numbers that are given in this question to calculate omega. But you need to realize the question is asking us deduce whether the person will slide down. So we need to compare this with reality. This is the required value of the angular velocity so that the equilibrium is maintained. Now, in reality, with that 20 revolutions per minute, that's giving us the frequency per minute. So since we know omega is 2 pi over t, it's also equal to 2 pi f because f is 1 over t. So I can rewrite this as 2 pi. We have 28 revolutions per minute, so I'll write that as 60 seconds so that it's an SI unit. So what do we get when I calculate this? I get 2.9 radians per second. So what I need is a minimum of 2.6 radians per second angular velocity, and the actual angular velocity for that frequency is 2.9, so the person does not slide. Okay? 10a is a definition what is meant by gravitational potential at the surface of a planet. The gravitational work done per unit mass to bring a small mass from infinity to the surface of a planet. So potential is potential energy divided by mass. So you define potential energy, which is the work done to bring from infinity to the surface of a planet. So since this is per unit mass, what you define potential energy work done from infinity per unit mass makes it the definition of potential. 10b, we're asked, after being given some values here, mass of Venus, radius, the mass of the projectile we're launching, and the initial speed of launch. Now, we're given that it calculates to a 1.1 times the escape speed from that planet. To find the kinetic energy, we can use the good old 1/2 mv squared for kinetic energy. We have the mass of the projectile for this, and 1.1 v escape. This is supposed to be squared. So what I do, 1/2, I can use this mass, which is 3.5 times 10 to the power of 3. Since I'm squaring this, I would be squaring the 1.1 factor. And since escape velocity is given as square root of 2gm over r, the square of that would be g, mass of the planet, which is Venus, which is given as that number, and the radius of Venus, which is also given here. Substitution of these numbers, calculation gives us 1.04, sorry, that would be the speed. I'll just write the answer directly for the whole calculation. This is 2.27 times 10 to the power 11 joules. To describe the subsequent motion, so what happens when you launch a mass from the surface like that? Well, it will be moving away from the planet, where acceleration, which is actually gravitational field strength, should decrease. As the mass moves away, as acceleration decreases, speed will also be decreasing, because kinetic energy turns into potential energy until it reaches infinity, because the initial launch speed is actually larger than escape speed, so this projectile will become free. Okay, next question. We have two arrows in the diagram showing two stars and the planet which is in the gravitational field of both stars. That's the vector for the gravitational field of this star at the planet's location, and that vector is the gravitational field vector from that star at the location of this planet. The star masses are equal, the system is symmetric, the angles are given. So first we're looking for the gravitational field strength at that position due to one of the stars. So since we have a distance of 6 times 10 to the power 11, so that's to show on the picture, that's 6 times 10 to the power of 11 meters, and we know each star mass. So G, which is the value given in the data booklet table of contents, first row, mass is this. The R you would use from planet to each star is this. So basic substitution will give 3.71 times 10 to the power of minus 4 Newton per kilogram. That's the value of each vector. Then in part B, we're asked to find the resultant. Now, I copied a quick sketch of the same diagram here. Now, we now know the value for each of these G's. We know they're equal because the masses of the stars are equal and the same distance from the planet. To find the resultant of two vectors, we're going to use our good old knowledge of vector addition and components. So each of these vectors have, well, on paper, horizontal components, which will be equal and opposite, so these will cancel. And they have vertical components, which are equal and in the same direction. Now, arranging this vertical component for each G, since this is adjacent to the 34 degrees, this will be G cosine 34. But there's two of these, so the total resultant will be that. So all you have to do is multiply 2 by that number and cosine of 34 only to get a total resultant value of 6.1 10 to the power of minus 4 newtons per kilogram. Next question. What is meant by gravitational field strength? Gravitational field strength is defined as force acting per unit mass. Well, in an exam, don't write it as a formula like I just did. Use actual words, please. But it's defined as force per unit mass exerted on a point or small or test mass. Now, 12b again is a show that question. So we're supposed to end with this and relate from the formulas that we have in the data booklet. So since we're relating potential and gravitational field strength, we have these. We have gm over r squared for the G, and for gravitational potential, we have minus gm over r. Be careful about the r here. In the formulas, r is always measured from the center of each mass. So when the question says at a height above the surface, the total distance, this little r will be radius plus that height. So to show that to you on a diagram, if your height h above the surface, that would be the radius r. The distance in the formula will be r plus h at that location, and that's what the question asks us. Now, combining these two to write v in terms of g, I'm looking for this expression inside that expression. So you can do this algebraically any way you prefer, but actually the easiest way is to divide this function by that function, which will give you minus g over r for v. I'll rewrite here so you see it clearly. And then you put g as gm over r squared times r. You actually, when you put r plus h, and in here you substitute that for r and multiplied by r and the negative, you actually get the function that is required. Draw a graph to show the variation of the potential v by height above the surface of the planet. So there's a catch here. Normally we did this graph always like this, where this is the surface, okay? But this question says from the surface. So we start, the graph they want is actually starting from the surface. We're not asked to show inside the planet. That's why it starts from this intercept. That value would be minus gm over r, and obviously it increases, approaches 0 at infinity. 12D asks us to calculate the gravitational potential. Now we have this expression from above. Even if you can't make that link in the exam, now you might want to use V equals minus gm over r. However, you don't know the mass of the planet, you know, the radius of the planet and the gravitational field strength. So you have this and you have the r. Well, you would have to add these for the height, total height from the center, but you have these. You don't know the mass of the planet, so you can't use this. That's when you go back to your data booklet and you can find that. So in topic 10 formulas, you have gravitational field strength related to the gravitational potential as such. Rearranging this would give you that. So basically, you have a minus, you're given the gravitational field strength 2.2 times the sum of these numbers. So I'll write it as r plus h, where this is r and this is height above. So for the total distance, like I said, you have to add them. And then you calculate to find 6.0 negative 6.0 times 10 to the power of 7 joule per kilogram. Next part says draw given the path of an asteroid as it moves past the planet. So this asteroid was far away. That's telling us initially at 0. We're asked to find the speed of the asteroid, so we're obviously going to work with kinetic energy here. We want to use, remember what I always say, if you're stuck what to do in a question, either use a free body diagram, which won't help in this case, and we're asked to find the speed which relates to kinetic energy. So the second lead is energy conservation. Use energy conservation. Initial total is equal to the final total. So initially this asteroid is at infinities, where total energy is defined as 0, which means at P, at this location, the potential energy plus kinetic energy must also be equal to 0. In kinetic energy, we can find 1/2 mv squared. What do we write for potential energy? Now, you might want to use this, minus g m over r. And once again, we're stuck because we don't know the mass of the planet. But we also know one thing. This is given in the data booklet. This is m delta v. Well, actually, it's given as work equals m delta v, but the work is coming from initially infinity, so the potential energy at that point would be the work through that change. Using this expression, we can replace that with m times the gravitational potential at P. Rearrange this to say m times the gravitational potential equals a negative, since this moves to the other side, 1/2 mv squared. Divide both sides by m, and you actually get, since you know the gravitational potential is negative, we found that value above in the previous part, so you substitute minus 6.0 times 10 to the power of 7. That's equal to minus 1/2 v squared. These minuses will cancel each other. Put the 2 on this side, take the square root, and you actually find 1.1 times 10 to the power of 4 meters per second. And the last part, we're asked to find the gravitational force. Well, gravitational force is mg. All we need in this part is the mass of the planet, mass of the asteroid, which we actually have. So I can use that 6.2 times 10 to the power of 12. And the gravitational field strength, which is given above in the previous section. So multiplying those will give me the gravitational force in Newton. Thank you very much.